Okay, so in the final video of this section, we're going to go over the net change theorem and how we can use the depth and integral to calculate the displacement and the distance traveled of an object over some time interval. So the net change theorem comes from the fundamental theorem of calculus. And from that, we can say that the definite integral of the rate of change of quantity large f prime of x will give the total change or the net change in that quantity over the interval AB. So that means that, again, going back to the fundamental theorem of calculus, is if we have the derivative of some function, so here we have large f prime of x over the interval a to b. If we integrate this, we'll get that this will be equal to the antiderivatives of this evaluated at b and a. So this will be equal to large f of b minus large f of a. So remember that this is the derivative of what we get after we integrate this. So this is the derivative. This is the antiderivative of large f prime of x. So let's go through a practice problem because that's going to make it much easier to understand this stuff. So here we're given that a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is between 0 and 60. We have to find the amount of the chemical that flows into the tank in the first 20 minutes. So see, we're trying to find the total change in amount of chemical that's in the tank. So we want to find how much of the chemical flows in the tank over the first 20 minutes. And we're given the rate of flow of the chemical. We're given that it's 180 plus 3t. So we're given essentially large f prime of t, which is equal to 180 plus 3t. So if we have the rate of change of the quantity of the chemical that flows into the tank, then we can find the total amount of that chemical that flows into the tank over the first 20 minutes, because we can just simply set up this interval, an integral from 0 to 20 of 180 plus 3t dt. And then we can just use the first fundamental theorem of calculus to evaluate this. We'll get that this is 180 t plus 3t squared over 2. And let's go ahead and let's evaluate this. We're going to plug in 20 for t first. So 180 times 20 minus 3 times 20 squared over 2. And we plug in 0, doesn't change anything. It's not an issue. So 180 times 20, 3,600 minus 3 times 20 squared. So minus 3 times 400. So minus 1,200 over 2. Or whoops, plus 1,200 over 2. So plus 600. So then we'll get 4,200. In context, we're basically saying that 4,200 liters of the chemical flowed into the tank over those 20 minutes. Now, what's really useful about the fundamental theorem of calculus is you can basically apply this principle in all sorts of scenarios. And so you can apply it in, chemistry, environmental science, biology. Here we're dealing with the volume of water in a reservoir. So we can simply have our integral represent v prime of t, where v of t is equal to the volume of water, and integrate this. So it's really useful. We can even use it to calculate quantities in economics. Like if we have that C of X, the cost of producing X units of a commodity, then the marginal cost, which is also known as the derivative of C of X, can be calculated as this integral. So this is why you'll, if you ever wonder why you need calculus for some other subjects, it's because it's very useful because it's just math. It's applied in virtually every physical science. So now let's look at how we can calculate distance and displacement of an object. We're going to focus on a particle which is typically what you'll be given in your free response section of your AP calculus exam. So make sure you really take your time with these types of problems, because there's always usually at least one free response problem that's entirely based on, finding the distance or displacement of some particle over some period of time, or how much it changed position. And they're not simple. They're pretty tough. So really practice a lot with these types of problems. Okay, so another application of the net change theorem that we can use is to apply it to the velocity of an object or the velocity of a particle, because if we have that S of t represents the position of a particle, then velocity is a derivative of position, so velocity is S prime of t. That means we can integrate velocity over some interval a to b, and then we can find how much the position of that particle changed on an interval, because this will simply be equal to S of b minus S of a, because S of t is the antiderivative of velocity. So again, it'll be super useful. Looks like I'm running low on battery. Gotta make it quick. All right, so let's see here. So displacement versus distance. So displacement is essentially the same meaning in math or physics as you would think in real life, how much you change your position. So when we have a particle that's traveling, over some time period, we don't actually care about what distance it traveled. We just care about how much it changes position. Now, before we get to that, let's make sure we know and remember that if a problem doesn't mention like whether it doesn't mention the sign of velocity, meaning that it's moving forward or backward or left or right, we're going to assume that when velocity is negative, it's going to be moving to the left, and when velocity is positive, it means that the particle is moving to the right or it's moving forward. Left means backward, unless it says otherwise. If it doesn't say anything, make sure this is what any problem on an AP exam will represent. Okay, so it's displacement. So let's think of let's say of a typical school day. Let's say your displacement from 6 a.m. to, let's say, 10 a.m. So let's say you're at home at 6 a.m. and school starts at 8:30 a.m. And so you have to travel 5 miles to get to school, right? So let's just say you go 5 miles in one direction, just for simplicity. So your displacement from 6 a.m. to 10 a.m. is just 5 miles, right? Let's say we're plotting this point on an axis. Again, this is just for a hypothetical example. So again, if your school is 5 miles away and we're asking your displacement from 6 a.m. to 10 a.m., your displacement is 5 miles because you had to travel 5 miles. Your distance traveled is also 5 miles. Now, let's say what's your displacement from 6 a.m. to 6 p.m. And at 6 p.m. you're back at home because you finished school and you finished sports, so you're back at home. So you go back. You first went forward, you went in this direction, in the forward direction, in the morning, but then later in the day you go back home and you go to negative direction. So you end up back at home. So you go 5 miles in this direction, but then you go back 5 miles. So at 6 p.m. your displacement is 0 because your position is the same as it was at 6 a.m. Even though you traveled 5 miles to get to school and 5 miles to get back, your displacement is 0, but your distance traveled is 10 miles. So displacement can simply be calculated by just taking the integral of the velocity function on a to b. If we're looking at, of course, the interval a to b, the displacement can simply be found by integrating v of t dt on A to B. And if this, let's say this graph represents the velocity function, you're simply going to add A1 and A2. You're going to, since A2 is negative, instead of adding A2, you can say plus negative A2 or minus A2. You can treat A2 as a negative quantity and plus A3. So this will be your displacement equation. So remember, when a graph is above the x-axis, it's treated as a positive quantity. When it's below, it's treated as a negative quantity. So this is positive, positive, and negative. So it's simple to calculate displacement when you're given a function, because you don't worry about the sign of the function. Now, when you calculate distance, you care about the sign, because distance is always a positive quantity. Again, if you're traveling to school 5 miles and 5 miles back, if you were simply to integrate, that, you would have a displacement of 0. And if you were to treat that as your distance traveled, your distance traveled will be 0. So you can't simply integrate velocity to calculate the distance traveled over some interval. Instead, you always want to make the velocity function positive. So the total distance traveled by a particle on A to B will simply be the integral of the absolute value of v of t dt on A to B. So if we're talking about this, it would treat A1 as a positive quantity, it would treat A2 as a positive quantity, and it would treat A3 as a positive quantity. So what would happen in this is that you kind of think of this as a mirror. It will be mirrored across the horizontal axis. A2 would be over here. So you would find that. Now, calculating this is going to require more work, because you have to find when the velocity function is negative and break it into 3 intervals. Unless the function is very simple and you can easily calculate the absolute value of it, but usually it won't be. So let's go through an example problem, because it's always the best way to learn how to calculate this. Okay, so we're given the velocity of a particle moving along a line with the equation v of t equals t squared minus t minus 6. We want to find the displacement on the time interval from 1 to 4. Okay, so again, that's simple. We simply just set up the integral from 1 to 4 of t squared minus t minus 6 dt, and use the fundamental theorem of calculus to evaluate this. So we'll get t cubed over 3 minus t squared over 2 minus 6t from 1 to 4. And let me just go to the next line to make sure I don't cram. So we'll have 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. Four cubed, 4 1664 over 3 minus 16 over 2, so minus 8 minus 24, 1/3 minus 1/2 minus 6. And we'll get that this will equal, I guess we're going to have to break this into fractions, make them all over 6. So this will be equal to, let's first one, 128 over 6, 48 over 6. 6 times that, so 61, 144. All over 6 minus 2, 6, minus 3, 6, minus 36, 6. So if you caught on so far, integrals can be pretty tedious. So really concentrate when you're calculating it, because a lot of times you may just mess up on the algebra, which is it'll be frustrating. So 128 minus 48 minus 40, negative 64 over 6. Whoa. Minus negative 1, negative 37. So plus 37, so then it'll be negative 27 over 6. So 55, 4, negative 4.5. Okay, so the particle changes position by 4.5 feet to the left. So you can write that as moved 4.5 feet to the left. That's kind of how you would interpret that. However, this doesn't tell you how much distance it covered over this interval, because it could have moved 100 feet to the right and 100 feet to the left and 20 feet to the right. It could have been bouncing up and down. So to find the distance traveled over this interval, we want to calculate where the particle will be, where this function will be negative and where it would be positive. So let's draw a sketch of this. And usually when you're given problems like this on your exam, they really won't be that complicated, but just beware, make sure you know what you're doing. So this is a parabola, and this graph is going to look something like this. And we're going from 1 to 4. So let's say that's 1. We're gonna have a point here. 4 is gonna be past. So this will be a 4, 0. This will be a 3, 0. So we're looking essentially at this region bounded by the horizontal axis. So this is our V of t. This will be our t-axis. This will be our v. Now we just calculate where V of t is equal to 0. So we can simply just factor that. I kind of already gave it away. Oh wait, this is not a 3, 0. We're going from 1 to 0. Let me just work through just to reinforce my answer. So V of t, find where it's equal to 0. So using algebra, we just factor t squared minus t minus 6 as t minus 3 times t plus 2. So then your zeros are going to be you have t is 3 and then t is negative 2. So at this point that'll be 3, 0. And this will be negative 2, 0. Now this side doesn't matter anymore because we only care about this area. So you can see here that the integral is negative from 1 to 3, and the integral is positive from 3 to 4. So what we do is essentially break the integral up into two parts. We're going to have our integral be set up as the distance traveled will be equal to the integral from 1 to 0, or sorry, 1 to 3 of t squared minus t minus 6 dt plus the integral from 3 to 4 of that same function, t squared minus t minus 6 dt. However, whatever quantity we get here, we're just going to make it positive because this is going to end up being a negative quantity. So that's why we can put the absolute value signs afterwards outside of that. We evaluate this as normal. We're going to get some negative quantity, which is here, and we just then change the sign and make it positive. This is already going to be positive, so we don't have to change it. So we're going to have the same antiderivative expression. So what we're going to get is then t cubed over 3 minus t squared over 2 minus 6t from 1 to 3. Again, this entire expression will be positive once we calculate the number, plus t cubed over 3 minus t squared over 2 minus 6t from 3 to 4. Now this is really just algebra now. So evaluating this, working it out, I'm gonna try not to spend too much time, just kind of, you can pause it and work it out and if you want, and then check your answer. But this will equate to, working, powering through this will be 3 cubed, so 27. 27 over 3 minus 9 over 3 minus 18 minus 1/3 minus 1/2 minus 6. So it'll be the absolute value plus 4 cubed (64 over 3) minus 16 over 8 minus 16 over 2 minus 8 minus 24. Plug in the 3 in. 27 over 3. So 9 minus 9. Minus 9/2 minus 18. Oops, and a little bit here, I made a mistake. This would be 9/2. Oh, that would have been bad. All right, so time traveling, this will end up being the absolute value of negative 44 over 6 plus, and then this will end up being 17 over 6. And so then we just make this positive 44 over 6. So it's positive 44 over 6 plus 17 over 6, which will be 5161 over 6, will then be our answer. So the particle traveled 61 over 6 feet over the interval 1 to 4 seconds. All right, so I hope that helps. So good luck.